All right, welcome back, everyone. Hope everyone had a good lunch. Welcome to the server track and engineering forums. I'm John Stewie, the co-lead. And our first track up is the SmartNIC data plan acceleration with Nick Flume.
Hey guys. So today I'm here to talk about SmartNIC data plan acceleration and reconfiguration. Most of what I'm going to focus on today is actually going to be more on the reconfiguration side. This is something we're starting to see. It's something customers talk to us about a lot. It's something which I've had 5 or 6 conversations about actually in the last day and a half here, which is great. We can get these NICs in. We can add, sorry, it's running ahead of space there. We can get these NICs in. We can do these things. We can add all these features, but how do we keep reconfiguring them? How do we keep changing them, the model of use? And 3 or 4 years ago, we would never have been having this conversation. 3 or 4 years ago, I'm sorry, we're starting to have we have a technical issue where the slides keep running forward. So apologies. If things start running forward, just somebody grab me. So 3 or 4 years ago, we wouldn't have had this conversation. 3 or 4 years ago, you had everybody saying, well, we can just use CPU and we can keep using CPU. Now, suddenly we have all kinds of hyperscale vendors telling us all about the acceleration they're using in different use cases, networking, storage, machine learning, whatever the use case is. There's a huge amount of acceleration, accelerated processors out there. You know, Amazon have shown off their Annapurna SmartNIC. Microsoft have over the last couple of years spoken significantly about their Microsoft Azure SmartNICs. So this is really something which has come in. And at the moment, it's focused very much at the guys who have large R&D budgets. They can, you know, Microsoft can hire up all their own Verilog programmers, which is great. If you have your own Verilog programmers, you can keep reconfiguring your FPGAs, you can keep writing new code for them, but not everybody's going to be able to hire up enough Verilog programmers to be able to use that model. So we really need to think about how we're going to get to the point where the rest of the market has a model where they can independently program their own SmartNICs using off-the-shelf solutions. So just to give you an example of what kind of architecture options there are out there, you've obviously got the TCAMs and FPGAs, and then you've also got sort of ARM, MIPS. Yeah. We've got ARM CPUs, we've got MIPS CPUs which get used, and what we have in our use case is the network flow processor. The network flow processor is a programmable run-to-completion model chip, which has highly multi-threaded. So we've got 8 threads per core, and we have between 72 and 120 cores on there. And these are fully programmable, so you program them in effectively what is C. Let's check if this thing, yep, still working. You program them in C, and you're able to do very flexible types of network offloads. And an example of an application we run through there is OVS. This is just to give you an example of the kinds of savings you're making. So if you compare us to kernel or user OVS for a couple of use cases, you can see you get significant performance gains and significant efficiency gains. So you're saving power, you're saving CPU, and you're able to do more per server. The use cases driving these types of deployments, we have NFV infrastructure, we have security, and obviously we have the hyperscale cloud networking, which is really what we're focused on here. But as I said, these deployments at scale need a new level of interaction between the firmware and the software, because we can't keep updating our software without updating our firmware. At the moment, you can use your drivers, you add things into the driver, you add new bits of work there if you're using what is sort of a standard NIC. But as soon as you get to the SmartNIC model, that breaks down because you need to keep updating things. You can't just keep updating your Linux kernel, because if you're offloading OVS and the OVS is changing in the kernel, then we need to actually update the firmware as well at times. So we need to think about stable models whereby we can update the firmware as we update the software. And this interaction is something which has come up a lot this week. Actually, I think the guy from Ericsson has got a talk going on about a similar topic at some point today. AT&T have spoken about this. We've seen this come up in the presentation which Facebook did as a keynote yesterday. This is something which is coming up a lot. So we need to really think about how we implement a DevOps model to be able to use this type of functionality. So there are really different models for how you can do this. So obviously there's the fully custom targeted application. That's the model which you can use if you're using FPGAs, if you have a large team, And then you do get highly flexible offload, which is optimized for your particular use cases. But as we say, not everybody can use that anymore. You also have transparent offload of applications. So these are things like OVS. KTLS is something which is coming up in the future. These are the types of offloads which people can use where it's application specific. But that obviously ties the consumer to an application. It means that if you use a specific type of offload, you can't flip it tomorrow unless you have some form of programmability, unless you have the ability to program the firmware on the SmartNIC. And then we have the final model, which is, so this actually got spoken about in Facebook's keynote yesterday. They spoke about bytecodes and how they're using different bytecodes to be able to accelerate different types of processing. The bytecode we have in the networking space, which is what I'm focused on, and this is actually what I'm working on at the moment, is called BPF. This used to be the Berkeley Packet Filter. It's now something totally different. It's effectively a kernel-based virtual machine, which can do lots of programming. It's used for DOS-type filtering. It's used for load balancing. There's actually even talk at the moment where VMware are busy working on implementing OVS as a BPF program. So this is somewhere where there's a significant amount of traction at the moment in the Linux kernel community. And this is something which we've focused on offloading. And it gives us a way of effectively offloading a bytecode. And suddenly you now write bytecode for your server. You don't care if the NIC is there or not. And you have a fully flexible way of writing accelerated stuff for your server, and then suddenly it is able to be offloaded to the NIC. Now this gives us a model which is pretty transparent, pretty clear, and gives you a very simple way to enable acceleration without actually needing any extra resources. So how does it work? How can you do that? So this is just a quick example just to show you on a very high level. And if people want to catch me afterwards and drill down into specifics, I'm more than happy to do that. This just gives you a very high level overview. So effectively what happens when you use a bytecode? So you write your program, let's say in C, you can actually write it in P4, in Go. There's actually a Lua JIT as well now. So there's a huge variety of languages you can write in up at the top. We don't care. That then goes through a compiler. It can be LLVM. Sorry, I don't know where that space is coming there. Or it can be BCC. It can be a couple of the other compilers now added in as well. You then pass the program down to the verifier. Now, this is part of what provides the safety when you're using this model. We have the kernel-based verifier.c. This is a piece of code which allows you to check in the kernel that the bytecode is safe. So this ensures that there aren't things like infinite loops, which can never be broken. There aren't a variety of things which would cause your kernel to hang. And so this gives BPF a very strict safety measure to be able to run anything. And this allows you, as the operator, to be trust in it. And this is being used by hyperscale data centers today. Some of them have been very public about it. So this is a safe way of doing things. What we've then done is usually you would then, from the verifier, your program would go through the x86 JIT. And from there would get passed down to the host CPU. Now what we've done is we've upstreamed into the kernel, we've actually upstreamed our own JIT. So now you can push your bytecode down into the kernel, it gets checked by the verifier, and then we actually have our own NFP JIT, which translates the bytecode into our NFP assembler. So we're effectively using the compiler, which is you're already using, and then we're just translating the bytecode. A thing we've added with that is we then reuse some of the infrastructure in the verifier to make sure that it is safe for offload as well. So you have an extra level of checking on top of the checking you've already had. This then provides you with a very, very flexible interface, which works exactly the same way it would work without having the acceleration there, to be able to add that acceleration. This just gives you a little, just a quick little jump into the firmware, so you guys can understand what's actually going on the NIC when you do these types of reconfigurations. So let's say we are just running BPF. We effectively have specific cores. So out of the between 72 and 120 cores we have on there, we have a set of them which are divided up to use BPF. These cores then actually go and this gets translated down. So the JIT will translate the instructions down into these cores. And we also have other cores on there running what we call our basic NIC flow processing cores. They will run any basic NIC offloads so that it's consistent with any use case you have whereby you're using standard NICs and running your BPF in the kernel. Because the problem is unless we do all the standard NIC offloads, you're going to have a consistency problem. things are actually going to look different when you do the offload. And the whole aim of this whole process is to ensure that the offload is exactly the same as what it would look like if you were running things in the kernel, apart from the fact that you get your CPU back. And if we want to, let's say we reload a BPF program, we are then able to dynamically one by one switch these across, these islands. So we have the islands which have 12 of these flow processing cores on each, and we're dynamically able to switch the islands across to the new flow processing regime. Now, this gives us the ability to always ensure that your packets are being processed. At times, the performance as we do the switch will be a little bit slower, but that's milliseconds. So this is something which allows us to fully reconfigure things on the fly, totally flexibly. But we obviously need to get beyond this model, because this is great if you're building things in BPF, but what if you have a use case where you are building custom kernel code, or sorry, not custom kernel code, custom firmware code, or you are offloading an application in the kernel? We need to understand, and we need to build up a model which doesn't just work for Netrunner, doesn't just work for us, but works for the whole community. All the other SmartNIC vendors out there who are starting to pop up. We've had a few announcements the last couple of days, and we have others out there already. Unless we have a system which works for live firmware reconfiguration for everybody, we're going to struggle to be able to deploy these in huge scale. So that's a key thing which I think is very important in the long run if we want to deploy SmartNICs within the OCP model. So we just have some very simple proposals which we've started pushing out there into the community. So we've started working on these, and we've started pushing these out, and they are out there ready for comment today. These have been submitted to OCP. So the first question is, what if you have your NICs running in what we call a bare metal mode? So there are two options for this. This is if you have a data center, and effectively you're just your data center provider, the guy who's putting together your servers. He is just throwing NICs in, and he's shipping these across to you. He doesn't know which firmware you want. You've got different firmware configurations which go with different NICs. So he's just sending these without any firmware on them, just throwing them into the servers and shipping them across to you. First, you need to be able to actually reconfigure your firmware once those NICs get in place. And you will have different firmware in different places which you want to actually add onto the NICs. So for that, you need an update model whereby you can assume that there is nothing on the NIC. And by the way, this also works if you end up deciding you want to use these NICs in a configuration whereby they're not actually attached to a server, which is another possibility which we haven't explored fully in this presentation, but that's something which people could use. This gives you the ability to be able to effectively over the network update the drivers, update the firmware, and update these NICs. We've also added in some features for security and to ensure that this is not a vulnerable spot. So there's some talk and some work we need to do in the community to ensure we take that further. And then obviously there's the second half of this, which is, let's say we have a NIC in deployment, it's already running on a server, and we want to have a pretty simple model to be able to update this. So what we have here is a set of sort of blocks everywhere, but effectively this comes down to a bunch of tools which are mainly already in the NICs. We just need to add a couple of extra features. So when they're talking here about a firmware loader, effectively you can use eth2 to flash your NICs. So that's already a partly solved problem. We just need to add a bit of feature. There's a feature gap there which we need to cover. And then in terms of where the data plane function packages run, obviously Linux already has a firmware repository. So if you upload your Linux, there is a firmware repository there as part of your Linux build. A key problem though is that that doesn't tend to be kept updated. So you have all these updates happening with your kernel, if you're running in the kernel, and then suddenly you need to actually be able to update this as you go along, and you need to be able to keep that in the same state as your kernel. Now that's where a key problem comes in, and being able to actually manage this and have a system which configures this and runs this on a higher level is fairly important. And that's effectively why we have started this conversation. I think there are other people out there who are proposing solutions, and I think the key thing here is not that we say one way is the best, another way is the best. We just need to work together and work out what is the way to do this, because I think it's something that a lot of companies and a lot of people will need in the future. And so just to summarize, keeping it pretty short because I want to save a bunch of time for questions. SmartNICs obviously add a bunch of flexibility and reduce your cost of ownership of your data center. This has been shown by hyperscalers. This has been shown by people who have actually used this technology and have this technology and have really shown significant performance benefits from it. However, obviously, stability and maintainability is a huge thing when you're running these types of data centers because anything that can go wrong will go wrong. That's just the way it is. And so we need to ensure that we're able to apply these in a way that allows people to have that confidence that SmartNICs and acceleration will be stable and will be safe and will be maintainable. So we have started working on this in the community. Obviously, there's a bunch of work going on in the Linux community about this. This is where the NFP BPF JIT fits in. There's the update problem is a significant debate that's already happening within Linux, and this goes across different spaces. So there's a significant chat about how we update things for IoT. There are IoT devices that need updating. There is firmware in accelerators that needs updating. There's a significant bunch of components which are becoming part of what is the next generation of the internet, which we need to actually be able to update the whole time. Because if you have a bunch of components running in there, which are running unstable components, which are out of tree, slow at being updated, and running old versions of Linux, that can cause significant issues and significant safety problems and security problems. We have, as I said, we have the Iconics guide, which has come out as a first proposal. And then beyond that, visit our booth if you want to check out some early demos of the eBPF-based data plane. And then also, there's a few other demos there. I want to keep things pretty short because I want to be able to leave some time for questions. And I also want to be able to gather some feedback. So if anybody has anything, I think I also have some links which I would point you to. These are such as the talk we did in NetDev, which is the Linux Kernel Network Development Conference, about eBPF offload. We also have demos which are online, as well as the Iconic specification. OpenNFP is where we have a lot of resources for academic projects. And then finally, if you want to actually get your hands on one of these to start playing with it, I have the links there. So that'll be it from me. Thank you, guys. Any questions?
Questions, anyone?
Can you comment on which versions of the kernel are supporting which aspects of this?
So we updated this, we upstreamed this into 4.9. So 4.9, we are within TC and XDP offload. So that's already there. And then 4.10, obviously, it's there already. And we're upstreaming more things as time goes by. So there's going to be more and more features coming in. That goes in through NetNext. Okay. So that goes in through Dave Miller's tree. And that's where we really push things into. And that's where a lot of the debate happens. And that's where a lot of this work is taking place at the moment. So a key thing, which I haven't spoken that much about in this presentation, is which allows a lot of this to happen, is XDP. XDP is the Express Data Path, which we've added into the Linux kernel. This effectively allows you to do a lot of work before you even get to adding an SKB to the packet. This means that suddenly a lot of the infrastructure that goes with Linux, you can actually do your work before it gets to that point. Now, this is very important, especially if you're doing things like denial of service protection, because suddenly you can drop packets much faster. Now, that sounds stupid, but that's actually a really important use case. Because if you're a huge data center, you are going to get DOSed every day. And so this gives you the ability to drop significantly more packets. Kernel-based examples get you to about 20 million packets per second per core you're able to drop. But that's without any matching, without any of that type of work. We're able to get significantly higher with that, with the actual DOS program running in full. So this gives you a significant advantage over what you can do if you're dropping in TC, where I think you can hit about. So again, these numbers should be probably divided by about 3 to give you the accurate number, because in TC you can get, if you just touch and drop, you can get, I think, about 4.8 million packets per second. But you need to actually take these numbers and then actually build the whole program around them, do all the matching. So that will significantly reduce the rate you're able to drop at. We're looking at the NIC to be able to give you an example, we're looking to be able to drop at about 30 million packets per second with the entire program running, potentially even higher than that. So we have a significant improvement in that space, and this is one of the first use cases we're looking at.
Can you talk about some of the other use cases besides sort of packet filtering that this language can be used for?
Yeah, so just to talk about some of the other use cases. So there's a significant amount of use cases. In XTP and TC, most of them are networking. So in the networking use cases, we have things like virtual switching. So VMware has a team working on this. And they've been very public about this, working on BPF-based OVS. So that means that instead of having a kernel module for OVS, suddenly OVS is able to run purely through these BPF programs. Then another use case is load balancing. That's something which a couple of people have worked on. So this is taking things like the IPVS load balancer, which is part of the Linux kernel, and then actually implementing a subset of that within BPF. Other use cases, which I can think of on the top of my head, I'll leave it at that for the networking side.
Things like crypto in scope, or that have more complicated?
So crypto is something which people have spoken about. It's not been added yet. So there's a series of helper functions which get added, and they basically help you do these types of things, such as you'd effectively have a crypto call and have a look aside to it. That's something which hasn't been done yet, but it's certainly not something which is out of the question. That's something which KTLS, though, is being proposed for at the moment in the kernel. If you know KTLS?
No.
Okay. Yeah. And so that's something which is pretty significant. Then other use cases, there's a lot of tracing use cases. So network tracing. So there's a guy called Brendan Gregg at Netflix who's doing a lot of work on this at the moment and building up a whole basically debug system based on BPF, so that you're able to do a lot of network tracing and a lot of work actually to figure out what's going on with your network. Because, you basically, if you're running a large data center and suddenly there's a problem, you've probably got 10 minutes to work out what the problem is, if that, before everything dies. I mean, you're lucky if you've got 10 minutes. And in that time, if you just have ping and trace route, it's pretty hard to get something done. So he's actually built a huge library of tools in BPF, and you can check those out. They're all up on his website. If you search for Brendan Gregg, you'll find them. And so that's another very significant use case, which people are using it for.
All right, any last questions? Okay, thank you, Nick.
Thank you.